Last time I recorded to the cloud and I was like, I think I didn't record this lesson. And then it popped up in my email about 30 minutes later. I didn't tell you until I really figured out what was going on. All right. Do you know it was a bad idea?
Mount Rushmore.
Yes, but also not as bad of an idea as that. But eating spicy ramen right before this lesson. My lips are on fire.
But which spicy ramen did you eat?
Not shim black, but just regular shim.
Okay. They also have tonkatsu, which is like not so bad, and it's less spicy because you just use like spicy oil. It's like that. It's like pretty good.
Is it like less salty? Or is it just as salty? I'm always looking for ramen that's like not necessarily as bad for me as ramen usually is.
Well, you just put less of the packet in.
Yeah, but I want all the packet.
I see.
But my lips are on fire right now and I have a little bit of indigestion, so let's do this thing. Was that enough of a cliffhanger?
I don't know.
What did you have for lunch today, Mrs. Contreras?
I didn't eat lunch today.
I was like, so sorry, third period, but I didn't eat lunch before third period today, and my brain was like not functioning. And then I made it through third period, and I ate my my ramen. All right. All right, let's get started with some math.
All right.
Let's title our page. What's the date?
Monday.
And what's the period?
Yes. Post-Cambrian. What is the actual period? There is like an archaeological period or something.
Oh, are we in the Anthropocene? I think we're in the. I don't know. There's a podcast listening to called Anthropocene Reviewed, where John Green, the author, reviews things from current life. It's pretty good.
I've listened to some of that.
It's only 20 minutes long, so it's a nice short one.
But it was like on a break too for a while, right?
Yeah. I think so. I don't know. Seasons. Who knows? All right, let's go ahead and do math.
It's unofficial.
Polar form of complex numbers. So we just finished talking about complex numbers. We have extended our number line into a complex number plane. We have a new dimension that we can work with, the imaginary dimension. And these numbers have a function. When you multiply by 2, you are dilating a number away from the origin of the number line by 2. When you multiply by a complex number, you're doing just about the same thing. There's a rotation involved, though. What was that rotation if you multiply by I?
180.
Be careful. No, you just told me 90. -1. 90. Because I squared is -1, the 180-degree rotation. See, right. So we have a polar form of complex numbers. Now let's go through these bullets real quick. Some of them do contain questions. Actually, only one of them does. So far, we have associated the complex number a plus bi with rectangular coordinates a, b. 2 complex numbers in rectangular form are equal if and only if their real parts are equal and their imaginary parts are equal. Why is this?
Because there's only one way to represent rectangular coordinates.
Yeah,
you don't get repetition. Like in polar, we have many ways of expressing the same location.
What allows us to, why is that? In polar, can we express a location in multiple ways?
Because we have angles where we're getting the same angle again. And then the negatives give us reflections on those angles that we're using.
Exactly. So we have this complex plane. There are locations in this complex plane. Those are complex numbers. We can represent those numbers in non-unique ways using a polar coordinate, a distance from the origin of our complex plane, and our angle from, I guess, the real positive real axis, that first axis that you learned in like first grade. Let's what do these other bullet points say? We can also describe complex numbers in polar form. The absolute value, or the modulus, just some quick vocabulary, is represented by r. So that's the distance from the origin of the complex plane. The angle theta is called the amplitude or argument. That's your angle with the positive real number line. And then two complex numbers in polar form are equal if their moduli are equal and their arguments differ by a multiple of 2 pi. Okay. We are going to, proceeding forward, not give a modulus or an absolute value of a negative number. Is that cool?
Okay, sure.
We'll talk about its absolute value as a positive number. And if we want to be like in the third quadrant of the real plane, we'll just have an angle between 180 and 270.
Sure.
We won't say like 45 degrees and then -2. We could, but that's generally not done. Okay. The polar form of a complex number is what we've done before. X equals r cosine theta and y equals r sine theta. So if you have an A and a B, we can convert to polar. Right? I haven't explicitly told you how to do that. Can you help me write this number, -4 minus 3i, in polar?
Can we use this graph that we have?
Absolutely.
Okay.
I'll let you take the wheel.
So we have -4, so 1, 2, 3, 4, and then -3, so 1, 2, 3. So I'm going to drop a point there. Boom.
Bye.
Okay. So that means, and then just looking at that, since we have 4 and 3, that means that we have a 3, 4, 5 triangle, which is nice. So then we get r is 5.
Sweet. So how'd you do that conversion? You said 3, 4, 5 triangle. What would it be for like A plus BI?
Well, that would just be the conversion that we had from before, where r is the square root of a squared plus b squared.
Sweet. I'm gonna go ahead and add that on the side just as a tool for people in the future.
Yeah. So then all we got to do is find our theta, or our what do we call it?
Argument, or let me scroll up.
Amplitude.
Amplitude. To be honest, I just call it the angle.
Yeah, I think I would just call it theta. Like
Let's just call it theta. Let's just move forward. You know, that's what you'd see in a textbook.
Mhm.
If you open up the Larson, you'll see that. Larson, by the way, everyone, is the author of many of the textbooks we use at Blair.
Mhm.
That's what it says, but let's just go with angle, because what do you always say about math vocabulary?
What
Maybe
do
you don't
I
always
always
say.
say? Do I say
Yeah.
something?
I don't know.
I
Just
don't know.
as long as we can communicate between ourselves,
Mhm.
everything is good.
Yeah.
All right. Rant over. Sorry.
So how do we figure out what this angle theta is?
Can you draw a triangle for me on that purple point?
Absolutely.
I think I'm feeling the formula from polar.
Mm.
But we have a third quadrant angle, so we're going to have to add pi to it. Right?
So theta is equal to pi plus something.
Mm-hmm.
Okay.
So I think the formula for getting the angle for a negative x value, in this case that'd be -4, is arctan of y over x.
So I should have 3/4.
Yeah.
And those negatives don't matter.
Yep. Just chop chop. Pew. Yeah, I finished Clone Wars, by the way.
Oh, nice.
Yeah.
Way
A
ahead. of me.
lot of Netflix lately. Not good for me. So I think that arctan is going to be this angle that I've just labeled right there.
Okay.
And the pi is what it accommodates for this. So we're getting that angle. Pi plus arctan 3/4. Let's go ahead and figure out what that is.
My MATLAB is really slow.
All right, I lent
Yeah,
my
the
calculator to a student for the AP physics exam. So are we both calculatorless? Do you got it? Or
Rewind. 10.
I'll get my digital TI up for future reference. I feel like we should know what arctan of 3/4 is, because it's a 3-4-5 triangle.
Yeah, but it's like weird. It's 0.63. No, it's 0.643.
643. Alrighty. Awesome. So we can describe this coordinate as 5 cosine 0.643 plus I 5 sine 0.643. Can I write that out for us?
Sure.
So I'm going to use z for a complex number. We have 5. So let me do this. We have -4 minus 3i. And we have figured out that the x is 5 cosine 0.6435. Let me just do 0.64.
Do we have
Plus,
to add the pi to that?
we do. What is it? What is that plus pi? Woo, we almost had the first quadrant angle. Completely different complex number. 3.14 plus 0.64.
3.785.
3.785. Let's go to 3.79 plus I times 5 sine 3.79. Boom. That is the polar form. We still have two components, the real component and the imaginary component, but we're writing it with polar, and it's always going to be the same angle. That's how the polar form is constructed. Same angle, theta and theta. Sine gives you the y, cosine gives you the x, r dilates it to the right size. Boom.
Sweet.
There's another way that this is written. Have you seen it before?
I don't think so.
Sometimes people are lazy and write. Let me see if I can get this. Oh, that's not cool. Come on. This is annoying. 5 cosine I sine 3.79. 5 cis theta?
I have never seen that. But
You've never seen this?
No.
So this is just shorthand because it's always going to be cosine I sine. Same radial length, same, I think we called it modulus, and then same angle. So instead of writing this whole thing out, very often you'll see down here in this next example, cosine I sine of 5 pi over 3. This would be a little bit more useful when we learn more properties of the complex form, the polar form of a complex number. Cool. So 5 cosine 3.79 plus I 5 sine 3.79 is this number. Right? This number is nice because it tells us exactly how much we're dilating by and exactly how much we're rotating by when we multiply a number by it. 2 times 5 cosine I sine 3.79 is going to give you, I guess it'd be 10 cosine, whatever. Let's move on. Graph the complex number and express it in rectangular form. 4 cosine 5 pi over 3 plus I sine 5 pi over 3.
So can you just do the polar?
So our radial length is 4. 1, 2, 3, 4. And our angle is 5 pi over 3. That's just down here.
Wow.
Boom.
Beautiful.
Very easy. Let's express it in rectangular form. And that should be pretty easy too, right? X equals r, which is 4, cosine 5 pi over 3.
Yep.
What is that?
4 times a half.
1/2. 2. And then is the other one going to be, is it going to be,
2 root 3.
-2 or 3?
Yes.
So 2 plus I, and actually minus I, 2 root 3. Boom. And that's about right. 2 and -2 or 3. Good stuff. Cool. All right. Let's do some operations with this. Way back when I was like, how do we multiply 1 plus I times 2 minus 3i? Those numbers are made up.
We FOIL.
And we FOIL. How do we multiply 2 polar form complex numbers?
Well, is the dilation going to be grouped and then, but what should we do with the angle? You multiply the angle.
I like where you're going with this. The dilation will be grouped. So if I dilate by 6, then I dilate by 2, how much have I dilated?
12.
12. So let's hypothesize an answer. Let's conjecture an answer. If I rotate by pi over 6, then I rotate 2 pi over 3, how much have I rotated?
2 pi over 3 plus pi over 6, which is like 4 plus 1. 5 pi over 6.
Let's conjecture this as an answer. If that works, then things are beautiful. Let's bash it out though.
Okay.
Let's foil. All right. So let's do what you said. Dilate the 6 and the 2.
Mm-hmm.
But let's foil what we have left. 6 cosine pi over 6 plus I sine pi over 6. And then cosine 2 pi over 3 plus I sine 2 pi over 3. All right. First, cosine squared. That's not true.
No.
Cosine pi over,
of pi over 6, which is a number, times cosine of 2 pi over 3, which is a different number.
Thank you. First, outer plus I cosine pi over 6 sine 2 pi over 3.
Mm-hmm.
Sweet. Inner I sine pi over 6 cosine 2 pi over 3.
Nice.
Cool. And then last plus I squared.
So it's a minus.
That's an minus. Should I just change it now or next line?
I guess next line is responsible.
Yeah, let's just change it next line. Sine pi over 6 sine 2 pi over 3. Sweet. All right. Where do we go from here? What are your thoughts here?
This feels like we should be able to do some like sum of angles.
I'm feeling that too. Where is it? Let's deal with this I squared.
Okay. Cosine, cosine, sine, sine, sine.
I'm starting to see it. I squared. Let's write that as -1 sine pi over 6 sine 2 pi over 3. Do you see that?
Yeah.
Cosine, 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 sine, sine, sine. But watch this. Plus I cosine pi over 6 sine 2 pi over 3 plus I sine pi over 6 cosine 2 pi over 3.
So it's sine, cosine, cosine, sine.
Boom. Let's do some factoring. Boom. What's this first one?
That one is cosine of pi over 6 plus 2 pi over 3, which we established is 5 pi over 6.
Right there. And then plus I. And
that's sine of 2 pi over 3 plus pi over 6, which is
sine. Oh, but it's kind of backwards, right? Sine, cosine, cosine, sine.
Which is why I said 2 pi over 3 first.
So we get sine of 2 pi over 3 plus pi over 6. And it does exactly what you anticipated. It dilated by 12 and it rotated the sum.
That's so cool.
All right. Multiplying by a number in its polar form does exactly what you see in front of your eyes. It rotates that angle and it dilates the magnitude, the absolute value. All right. Should we show this for all expressions?
Or can we leave it as an exercise for the
Let's
viewer?
leave it as an exercise.
If you're confused, then watch what we did and then just replace all of the things with
boom
thetas and r's.
Instead of pi over 6 and 2 pi over 3, you got theta 1 and theta 2. Did you just say r's?
Yes.
I love it. All right, so we can show this for all values. So given the product between two complex numbers, what is that going to be?
R1, R2 times cosine of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2.
Boom. There we are. Quotient time. Let's do this one.
Okay.
Let's do this one. Okay. Find a rule for the quotient between two complex numbers. So let me write that out. R1 cosine theta 1 plus I sine theta 1 divided by R2 times cosine theta 1, sorry, theta 2 plus I sine theta 2. What do you think is going to happen?
I think we're going to get a difference,
Okay. Okay.
but I'm not entirely sure how.
I feel that in my bones too, because like multiplication usually leads to addition, like
Yeah.
with logs and stuff like that.
Yeah, it feels like exponent stuff.
All right, so let's just take this R1, R2 out.
Okay, because
And
those
then-
are scalars.
Yeah. Cosine theta 1 plus I sine theta 1 cosine theta 2 plus I sine theta 2.
Should we multiply by the conjugate
Let's multiply with the conjugate of what?
of the denominator?
Yeah.
So cosine theta 2 minus I sine theta 2.
Yeah, top and bottom?
Indeed. Because otherwise we're
Indeed.
breaking math.
Yes.
Can't do that.
Let's keep those R1 and R2s hanging. Flow time. Cosine theta 1, cosine theta 2. Probably should write theta before I write 2. What are we going to get here? What is I sine theta 1 times negative I sine theta 2?
That's going to give us a plus sine theta 1 times sine theta 2 because I squared is -1, but -1 times -1 is +1.
Cool. And then let's see, we got plus I sine theta 1 cosine theta 2. And then minus I cosine theta 1 sine theta 2. Woo! That's a lot going on the top. Ooh, but look at the bottom.
It's just going to be 1.
That's the most satisfying thing in all of math.
Well, let's explain why that is. So
Yeah.
cosine theta 2 times cosine theta 2 is going to be cosine squared theta 2.
Mm-hmm.
And those are the same numbers, so we can do that. And then we have cosine theta 2 times negative I sine theta 2, but then we're also adding an I sine theta 2 times cosine theta 2, so those cancel. And then we are left with I sine theta 2 times negative I sine theta 2. I squared is -1. -1 times that minus sign is going to give us a plus. And then that's our Pythagorean identity, which is 1. And then we're good to go.
Much happiness. Much happiness.
Sweet.
All right, sweet. So we totally got rid of the denominator. Always good to do that. R1 divided by R2.
So does that count as a denominator killer?
I think so. Pew, pew. All right, well, how about this top? I think we got it again. Cosine, cosine, sine, sine, sine.
We have cosine theta 1 minus theta 2.
Just as you conjectured. Plus,
I,
factor out the I.
mhm,
I think it's sine, cosine, cosine, sine.
Yeah,
We keep the minus this time.
and we have theta 1, theta 2.
Oh,
Nice.
So dividing a number by the polar form of a complex number, I guess, dilates in the opposite direction
Mhm.
and rotates in the opposite direction. Nice. So dividing by I rotates 90 degrees clockwise.
Oh,
Ooh, I've never thought about that before. That's interesting. So if I have like 2 and I divide by I should get, what should I get?
you should get -2i.
I think I should get -2i. Are these things equal? Multiply by I over I. Yep. 2i over -1, -2i. That's awesome. All right. Quotient, two complex numbers. We got
That is so
R1.
cool, Mr. Kirk.
I love it. I love it. I love polar form of complex numbers. I just think it's so interesting. And the next lesson, we're going to do some exponentiation. Get ready. All right. We got what do we have here? Cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2.
Yep.
Boom. All right. Can you find the quotient of these two numbers?
Yeah, it's going to be 2. I can't write.
Oh, you're writing it? You got it? All you?
Oh, no, you got it. You got it.
2.
I just found my pen. Yeah, you good. 2. And then we have cosine of negative pi. Right? Pi over
think so,
4
yeah.
minus 5 over 4,
Mhm.
negative pi. And then plus I sine negative pi.
Let's convert this to rectangular real quick. It doesn't look too bad.
Okay.
2
So
times.
we're 2 and then we're a negative pi. So
Cosine negative pi, that's negative 1, right?
yeah.
Plus I sine of negative pi, that's 0.
0.
Ooh. That's
Well,
weird.
are we writing it as just negative 2? Because that doesn't feel like rectangular form.
I guess we could do like plus 0i.
Yeah.
Yeah. But I like that. If these two complex numbers, the quotient of them is a real number.
Because it's taking something that's off of the real axis and then kind of like rotating it back.
Yeah,
onto
we're like 4 here. And we shrink towards the x-axis, the origin of the real complex plane. Real, imaginary. We shrink towards and we rotate 5 pi over 4. We're going to land right here, negative 2. And we were at something else. I don't know. We started at 4. I think that's going to be 2 root 2, comma 2 root 2. And we go down to the negative 2.
I like that it's like a.
That's the sound of dividing by complex numbers.
Oh, maybe we should make sound effects for all of the operations.
What's the sound effect for multiplying by a complex number?
Like the opposite of. Which is
Yeah.
Wow.
Explosion sounds.
Excessive.
I have been destroying your ears this afternoon, Mr. Contreras, and I do apologize.
It's okay.
There you go. There you have it. I believe that's where we close. Boom. Polar form of complex numbers.
Oh, you stopped the
Oh
screen
wait,
share.
I'll give it a. I was crabbed moments before or
Yay.
moments after I stopped the share. My intuition said, "Will not be crabbed today." I almost got away with it if it wasn't for you meddling kids. Let me stop my share. I say a lot of things I say what goes into my brain. Probably not the best. All right.
Okay.
Any words of wisdom?
Hmm.
Mr. Ocean, any words of wisdom for the ninth grade class, for the pre-calc students? We're filming a video. Oh.
Mine would be
on
listen to
polar
Mr.
coordinates.
Ostrander sometimes.
Wait, let me fix the speakers are fixed and microphone is fixed.
So I'm supposed to give advice. Does it have to do with polar coordinates?
It can be with about polar coordinates, or it can be about life.
It can be about life.
It can be about life.
Oh, about life. That's important. I would say the key thing, the key advice I can give you, because you guys are all thinking about what you're going to be doing this summer right now. I'm going to give you advice about the summertime. And the best advice I can give you about summertime is to have fun. And do the things that you enjoy during the summer. And make sure you have time for that. Because when we come back in the fall, you guys are going to have Mr. Rhodes. He's going to give you packets that are like 800 pages thick. I'm not trying to scare you. It's maybe a slight exaggeration, but not much. So this summer, you should enjoy yourself, relax, do the things you enjoy, go on bike rides, walk your dog. What do kids enjoy today? It's outside.
TikTok.
What would you say, Mr. Contreras?
They like TikTok.
TikTok.
TikTok. That's not, I would say, stay away from the TikTok. because the things that I've seen on TikTok, I mean, it's when I grew up, we had a crazy uncle or crazy relatives, and TikTok seems to be where all of those people go. So I don't know that I would hang out on TikTok a lot, because otherwise you're going to be getting bad advice from my Uncle Dave.
So there you have it, everyone. Go outside this summer. We're getting closer to the end of the year. How do you feel about that, Mrs. Contreras?
I think summer is a good time to have fun, but I would also say don't limit your fun only to the summer. You should always try to do things that you enjoy. And
Yeah.
if you're doing something you don't really enjoy, either try to do it quickly or pivot to something else.
Yeah. Awesome. All right, good video. Let's close this one out.